Hello everyone. Today we will discuss one more machine independent features of the assembler, namely control sections. And in the process, we'll also learn how multiple subroutines can be linked using the control section features. So first, let us see what is a control section. But control sections refers to parts of the program that maintain their identity even after the assembling process. That means that control sections can be independently assembled. They can be loaded and relocated independent of other control sections. Generally, control sections are used to represent subroutines or to indicate other logical subdivisions of a program. As I mentioned earlier, a programmer can assemble, load, and manipulate each of these control sections separately. So when control sections form logically related parts of a program, it is very common for an instruction in one control section to refer to an instruction or data located in another control section. This means that some means of control section linking is necessary when control sections form logically related parts of a program. Already I mentioned that control sections can be independently assembled, loaded, and relocated. Hence, the assembler generally is not able to process the references between the control sections in a usual way. This resolution of references between the control sections has to be delayed so that the loader is able to handle it at the time of loading the control sections into the memory. We refer to such references between the control sections as external references. For each external reference in a control section, the assembler needs to generate information to the loader so that the required linking can be done at the time of the loading. As I mentioned earlier, when control sections form logically related parts of a program, it's very common for an instruction in one control section to refer to an symbol defined in another section, or it may refer to an instruction or a data that is defined in another section. However, symbols that are defined in one section cannot be directly referred to by another control section. In order to refer to a symbol that is defined in one control section by the other control section, symbols have to be identified as external references so that loader is able to handle it at the time of loading the control sections into memory. So in order to identify those symbols that are defined in one section but that has to be referred in another section, we make use of two assembler directives, namely xdef and xref. Xdef stands for external definition. The use of an xdef assembler directive in one control section involves identifying the symbols that are defined in that section which can be used in other sections. I repeat, xdef is an assembler directive which identifies symbols defined in the current control section, but which can be used in some other control sections. And by default, all the control section names are considered as external symbols. In the sense, control section names can be referred by other control sections by default. Another assembler directive is xref, which stands for external reference. This assembler directive is used to identify those symbols that are defined in some other control section, but used in the current control section. I repeat, xref is an assembler directive that identifies those symbols which are defined in some other section but used in the current control section. In order to understand the concept of external references and the use of xref and the csec directive, we shall proceed ahead with by taking an example program which involves multiple control sections. Consider this slide. The slide shows a program consisting of 3 control sections. The first control section being main, the second control section addit, and the third control section subtract, indicated by the symbol SUBTR. The beginning of the program is identified by the assembler directive start, which also indicates the name of the program, that is main. The second control section, as I mentioned, is ADDIT, addit. You may see that these control sections are identified with the keyword csect. And the third control section is SUBTR, which is again identified with the assembler directive csect. The first control section begins from the start statement and it ends with the instruction x2 word 7, because following that the next instruction is addit csect, which indicates the beginning of a new section. Similarly, the second control section begins with the instruction addit csect and it ends at rsub. The third control section begins at the instruction subtr csect and it ends with the last instruction in the program, that is end first. Now we shall see the use of 3 control sections in the program. As you see, the first control section is named main, and the control section main defines 2 symbols, x1 and x2. x1 is a storage area of 1 word in length, or which is 3 bytes in length, which has been initialized with a constant 5. x2 is again a symbol that labels the storage area, which is 1 word in length and which contains the constant 7. Please note, x1 and x2 are the symbols which are defined in the control section main. You may see that symbols which are defined in the section have been listed with the directive xdef. Earlier we have seen that xdef is an assembler directive which labels the symbols that have been defined in the current section but which are accessible to other section. So by labeling x1 and x2 in the control section main with the keyword xdef, we mean that x1 and x2 are defined in the section, the current section, but can be accessed by any of the other sections, be it addit or subtract. Apart from these 2 instructions, x1 word 5 and x2 word 7, we have 2 other instructions in the program. The first instruction is first jsub addit. The instruction jsub causes a branch to the subroutine, namely addit. The second instruction is jsub subtract. So basically what we are doing here is, first we are calling the subroutine addit and then we are calling the subroutine subtract. Apart from this, there is one more instruction following xdef, that is xref addit subtract. So what is the use of this particular instruction? Please note that added and subtract are the two symbols which are not defined in the control section main. Instead, added belongs to the control section added and SUBTR belongs to the control section subtract, SUBTR. Since these two are not defined in the control section main, they have to be identified as external references for the loader. Hence, they have been labeled with the keyword xref. Please understand the difference between xdef and xref. Xdef is used to label all the symbols that are defined in a section which are accessible to other section. Whereas xref labels all symbols that are used in the section but which are defined elsewhere. Elsewhere in the sense in other control sections. Now we shall look into two other control sections, that is added and subtract. Added is a control section which is used to add two numbers defined by the locations x1 and x2. As you can see in the control section added, the first instruction is LDA x1, which loads the value of memory location x1 into register A. The following instruction adds the content of register A with x2 and store the results back in register A. The third instruction stores the sum of x1 and x2 in the location sum. Now, in the control section added, sum is the only symbol that is defined. What about x1 and x2? x1 and x2 are the two symbols which are defined in the control section main and not in the control section added. That is why we have labeled x1 and x2 using the keyword xref. Or in other words, all external references have been identified with the assembler directive xref. Now the question is, why didn't we label sum using the keyword xdef? It is because it just simply means that sum is not accessible to any other control sections. If the symbol sum is to be referred in any of the other control section, it has to be mandatorily referred or has to be mandatorily labeled in the control section added using the assembler directive xdef. Moving on to the next control section, that is SUBTR. This is a control section which performs a subtraction of the data in the locations x1 and x2. As in the control section added, we have labeled two symbols x1 and x2 using the keyword xref. What does this mean? This means that x1 and x2 are external references, or in other words, x1 and x2 are defined in other sections and they are used in the current section. Where have we used them? We have used them in the instruction LDA and sum. The instruction LDA x1 loads the content of register x1 into register A. Sub x2 subtracts the content of accumulated register. From the content of accumulated register, it subtracts the value of x2 and stores the difference in the register A. The third instruction, stadiff, stores the difference between x1 and x2 in the location diff. As in the control section added, please note we have not labeled diff using the assembler directive xdef. That is because the symbol diff cannot be referred in any of the other control section. It simply means that we are not using the symbol diff in any of the other control sections. If you want to use diff in any of the other control sections, namely main or in added, you will have to identify it as an external symbol using the assembler directive xdef. Now, you may refer that I have highlighted the instruction JSUB, LDA, add in the control sections main, added and SUBTR in red. Also, each of these instructions have been specified with the plus sign, meaning it uses a 4-byte format. This is because each of the instructions which are with the red font makes a reference to a symbol which is not defined in the respective control section. For instance, we have JSUB added in the control section main. However, addit is not defined in the control section main, which means the assembler is not able to assemble this instruction by using the actual value of addit. That is why you can't assemble this instruction using a 3-byte format, and we have to use a 4-byte format, so that the value of addit has to be fetched at the time of loading, and it has to be inserted at the proper location. Same holds for any other instruction which has been indicated with a 4-byte format and which is highlighted in red. For instance, in the control section addit, we have LDA X1. Why the 4-byte format is required here? Because X1 is a symbol which is not defined in the control section addit. Now, when you assemble the control section addit, you have no idea where X1 is defined. So you cannot assemble the instruction using the displacement. So a 4-byte format has been specified here. So we need to leave this, the assembling or the insertion of the address corresponding to X1 to be done at the load time by leaving appropriate command to the loader. The same thing applies to the two instructions here in the control section SUBTR. Okay, by now I hope the use of control sections in writing the assembly language program is clear to everyone. The use of csect directive is clear. Csect, as I mentioned earlier, is used to indicate the beginning of a new control section. And all instructions following csect until the next csect will belong to the corresponding control section. By default, all control section names should be treated as external symbols, which can be used by other control sections. And all symbols which are defined in a particular section, which can be accessed by other sections, has to be labeled with the assembler directive xdef. All symbols which are referred in the current section but which are defined in other sections should be labeled using the assembler directive xdef. So now we shall move on to see how an assembler handles a program that is written using control sections. Specifically, we will be looking into pass 1 and pass 2 of the assembler in handling the control sections, and see how the control sections can be linked together in the discussions ahead. As you all know, pass 1 has to do with assigning address to every instruction in the source program. As in the case of program blocks, an assembler maintains a separate location counter for each control section during pass 1. Also, when the control section is begun, the location counter is initialized to 0. I repeat, we have seen this, that location counters are separately maintained for each program block, and it was initialized to 0 in case of program blocks as well. So in the same way, we maintain a separate location counter for each control section. Now we shall see pass 1 processing for each of the control sections. Consider the first instruction. We have main start 0. So this indicates the beginning of a control section. It also indicates the beginning of the program, and the control section name is main. The starting address, as I mentioned, for each control section should be initialized to 0. So the first executable instruction, remember xdef and xref are assembler directives. They do not appear in the object program. They are just instructions to the assembler. We don't have translated form instructions for this. That is why the first executable instruction is first JSUB addit. So the location counter value for the first instruction is initialized to 0. The instruction is indicated by a 4-byte format. As you see here, we have a plus sign. So after processing JSUB addit, the next unassigned address will be 0004. So JSUB subtract will have the location counter value 0004. Again, we will process the instruction JSUB SUBTR. After processing the instruction JSON, the next unassigned address will be 0004 plus 4 because we have a 4-byte format here. So the next unassigned address is 0008. The next instruction is x1 word 5. So you may see that this reserves 3 bytes. So the next updated address will be 8 plus 3, which is 000B. The following instruction is x2 word 7. Again, this will occupy the instruction reserves 3 bytes of storage and initializes it with the constant 5. So the instruction, after this instruction is processed, the updated location counter value will be 000B plus 3, which is 000E. Moving ahead, the next instruction is added csect. Now, please note, the directive csect always indicates the beginning of a new control section, which means we have to maintain a separate location counter now for the control section added, and it has to be initialized to 0. So the location counter has been initialized to 0. The following instruction is xref x1 x2, which is an assembler directive not translated into machine language version. So you don't have to assign any address for this statement. So the first executable instruction, as you see, please note csect is also an assembler directive, so instruction will not be translated into machine language form. So the first executable instruction is LDA x1. This will be assigned the address 0000. After processing LDA, you know that LDA is 4 bytes in length because we have a plus sign. After processing LDA x1, we have the updated address 0000 plus 4, which is 0004. The next instruction is add x2, again indicated by a plus sign. So this instruction is 4 bytes in length. So the updated address is 0008. The following instruction is STA sum. Please note we don't have a plus sign here because sum is defined in the same section. You don't have to use a plus sign because the symbol is not defined elsewhere. It is defined in the same section, and you can calculate the displacement and assemble this instruction. This instruction is 3 bytes. You don't have a plus sign. So the updated address is 8 plus 3, which is 000B. The following instruction is sum reserve word 1, which reserves one word which is equal to 3 bytes of storage. So after processing sum reserve word 1, the updated address is B plus 3, which is 000E. The next instruction is rsub, and you know that rsub is 3 bytes in length. That is why we have the updated address after processing rsub equal to 000E plus 3, which is 0011. Please note this is also the last instruction in the current control section, because the next instruction is subtract csect, which indicates the beginning of a new control section. So again we initialize a new location counter value for the current section, set it to 0. The first instruction here is xref x1 x2. Again, this is an assembler directive, so the instruction is not translated into machine language form. So we don't have to assign any address. The very first executable instruction in subtract is LDA x1. So we assign the address 0. This instruction is 4 bytes in length. So after processing LDA x1, the updated location counter value is 0004. Similarly, process the next instruction sub x2, which is again 4 bytes in length. After processing sub x2, the updated address is 0008. Next, we process the instruction STA diff, which is specified using 3 bytes because diff is defined in the same section. This is 3 bytes in length. So updated address is 8 plus 3, which is B. The following instruction is diff reserve word 1, which reserves one word is equal to 3 bytes of storage. So updated address is B plus 3, which is 000E. rsub is again a 3 byte instruction. So the updated location counter will be 0011. The next instruction is end first, which indicates the end of the source program. And by the time we reach the end, the last location counter value, as you see, is 0011. Okay, which indicates the length of the control section subtract. So going back to each of the slides, each of the control sections, Please note that the last location counter value for each control section indicates the length of that particular control section. That means that the main control section is E bytes in length. Control section added is 11 bytes in length, and so also the control section subtract, which is 11 bytes in length. So that is all with the pass1 processing. We have defined all the symbols, we have assigned address to every instruction, and we have determined the length of every control section. Next, we shall proceed ahead with the pass2 processing of the assembler in handling control sections. Pass2 has to do with generating the object code for every instruction. We shall begin with the first executable instruction, jsub addit. The opcode for jsub is 48. N and I should be set to 11. That is why the first byte will be 4B. And this is a 4-byte instruction. After the first byte, we have the settings of flag X, B, P, and E. X is 0, B is 0, T is 0, and E has to be set to 1 because this is a 4-byte format. That way, XBP is set to 0001, which is 1. After XBP, what do we have? We have the direct address of the operand. Which is operand here? Operand is addit. But what is the value of addit? Do we know the value of addit? We are not aware of the value of addit in the control section main because it is not defined in the control section. And remember, I mentioned individual control sections can be independently assembled. That is why at the time of assembling the control section main, the assembler has no idea what will be the value assigned to the symbol addit. That is why we can't insert the actual value of addit. Addit is unknown. That is why we insert in the 20-bit address field the value 0, indicating that the value of addit is not known. Likewise, we assemble the following instructions, jsub subtr. The same logic applies to the next instruction as well, because subtract is not defined in the control section main. The following instruction is x1 word 5. Word is an instruction which generates a constant in 3 bytes. And what is the value of the constant? It is 5. So we represent it using the 24-bit 000005. The following instruction is x2 word 7, which again generates a constant 7, and the representation is shown here. So that is all with respect to pass2 processing for the control section main as far as object code generation is concerned. We shall discuss about the object program generation later. Moving on to the control section, addit. The first executable instruction is LDA X1. The opcode for LDA is 00, N and I are set to 11, so the first byte is 03. XBPE is set to 0001, only E is set to 1 because the instruction is a 4-byte format. And the operand here is X1. Please note X1 is not defined, it is an external reference. So you can't insert the actual value of X1, its value is unknown, so we insert 0. Likewise, we assemble the instruction add X2. Moving on to STA sum. Sum is a symbol which is defined in the current section. So we can assemble this instruction using a 3-byte format. In the 3-byte format, we assemble the instruction using the displacement, and displacement is the address of the operand, which is 000B minus the PC value. What is the PC value when the instruction STA sum is executed? It is 000B. So 000B minus 00B will be 0000. So the displacement is represented using 12 bits, which is shown here as 000. Last 3 digits indicate the displacement. And what is the opcode for STA? Opcode for STA is 0C. N and I are set to 11. That is why the first byte is 0F. Now, what about XBPE? XBPE are set to X is 0, B is 0, P is 1 because we have used program counter relative mode. And this is a 3-byte format, so E has to be set to 0. So we have 0010, which is 2. XBPE is set to 0010, which is 2 in hexa. The following instruction is sum reserved 1. Please note there is no object code generated because this is an assembler directive indicating 1 word of storage has to be reserved. The following instruction is rsub. Rsub has the opcode 4C. N and I are both set to 1. That is why the first byte is 4F. And we don't have any operand, so all the remaining half bytes are set to zeros. Moving on to the third control section, subtract. We have the first executable instruction LDX1, which is assembled in the same way as was done for the control section, add it. I'm not going to explain this again. Value of X1 is not known in the current section, so you insert zeros. Similarly, sub X2, we don't know the value of X2, so we insert zeros. All the instructions use 4-byte format here, so XBP is set to 0001, which is 1 in both the instructions. Moving on to STA diff. Diff is defined in the same section, that is why we get a displacement. PC is also 000B, and the symbolic operand diff also has a value 000B. So target address minus PC value will be 0. So that is why the displacement, 12-bit displacement, is indicated with 0. STA has a opcode 0C. You need to set N and I to 1. That is why the first byte is 0F. And we have used program counter relative mode. That is why P is set to 1, B is 0. So X, B, P, E are respectively 0, 0, 1, 0, which is 2. The following instruction is an assembly directive indicating that one word of storage has to be reserved. So no object code needs to be generated. It's just reserving the space. R sub is to be assembled in the same way as was done in the previous control section. Last instruction is end first, which indicates the end of the program. So we are done with the assembling of the instructions. So the next thing that we need to discuss is the generation of the object program. So in order to generate the object program, for the control section, I mentioned that control sections are parts of the program which maintains its identity even after the assembling process. So what does that mean? It means that we generate the object programs independently for each of the control section. We assemble each control section independently, and we also generate the object program for each control section independently. So we shall first see how the object program is generated for the control section main. The first record in the object program, as you know, is a header record, which begins with H followed by the name of the program. Name is main. Starting address for the first control section is 0. We have assumed that all control sections are having the starting address 0. So 0 is the starting address. And after that, we have the length. What is the length of the first control section? We have the length equal to 000E, which is indicated here. So after that, we have two new records being written in the object program. The first one is the defined record, and the second is refer record, indicated with the alphabets D and R respectively. So the record D is used to label all symbols that are defined in the control section, which can be used in other section. For example, you may see which are the symbols defined in the current control section using the source program and locating the directive xdef. So you may see that in xdef we have two symbols, x1 and x2. So these two symbols have to be identified in the defined record of the object program. The first symbol that we see here is x1. So I have written x1 here. In addition to that, we also have to indicate what is the value of x1 in the control section, in the current control section, that is in the control section main. So what is the value? You know that in the symbol table we will be having the value 0008 corresponding to the control section x1. So following the control section, the external symbol that is defined in the current control section, we need to place the value associated with that symbol. So following x1, I have to place the value 0008. Please note, we use 6 columns to indicate the control section, indicate the symbol name, and use 6 columns to indicate the value. So x1 is the name of the symbol, which is labeled in xdef, and 0008 is its value. Are there any other symbols in xdef? Yes, we have x2. So I have kept x2 following x1, And what is the value of x2? x2 is defined here. Its value is 000b. This will be saved in the symbol table during pass 1. So the value is 000b. So we are done with the processing of xdef directive. The next is xref. What does xref do? It labels all symbols that are referred in the current section which are defined in some other section. So all such symbols have to be identified in the object program to the loader through the refer record. So look into the format. The refer record begins with R, just as the define record begins with G, refer record begins with R. Following R, you need to list all the symbols that appear in xref directive. So we have two symbols here, add it and subtract. So I have written it here, add it in 6 columns and subtract in 6 columns. Following the refer record, we need to place the object codes as they are generated into the text record. So I have written the first text record here. T text record begins with T in the first column, followed by starting address of the object code. The first object code is 4B100000 and the address here is 0. So the starting address will be 0, indicated in 6 columns. Following that, we have to place the length. We don't know the length yet. I'll place this value later, which is the first object code. Object code is 4B100000. So we have kept it here, 4B100000. Following that, we have the next instruction, which is again 4B100000. So we have placed the next one. The next instruction is a constant, indicates the constant 5, which is 000005, 3 bytes. The next one is 7, 000007. After this, we don't have any instruction because this is the end of the control section. Apart from the text record, you may see that there are 2 modification records. So why is this modification record required? This is required because, please note, when we kept the object codes in the text record, you may see that in the address field for every instruction, we have inserted zeros. Why did we insert zeros? It was because we didn't know the value of the symbol add it or subtract, which are not defined in the current section. So we have inserted zeros. But at the time of loading the program into memory, the actual value of add it has to be obtained and it has to be inserted in the location that starts at this point. Where does the instruction begin? Please note the instruction 4B100000 begins at the address 0000. So starting address for 4B is 0. Next 10 begins at the address 0001. So you need to include one instruction to the loader saying that the actual value of add it has to be added at the location 0001. So we do that using the modification record. So modification record begins with M, followed by starting address of the field that requires modification. The starting address of the field that requires modification is 0001. And what is the length of the field? Please note the field here indicates the address field in a 4-byte format, which is 20 bits in length or which is equal to 5 half bytes. So the length is 5 half bytes. Following that, we need to indicate what is a modification to be done at the address 0001. What do we need to do? We have inserted 0 here because we didn't know the value of add it. At the time of loading, you need to add the actual value of add it. So I indicate it here using the command plus addit. Plus is a modification symbol which says whether you have to add something or subtract. Here it is plus, so we have to add the value of add it at the load time to the value, to whatever value is in the location 0001. Currently 0001 has the value 00000. Similarly, we have to do the same for the instruction subtract, because subtract is a symbol which is not defined in the control section, and we have assembled the instruction using the value 00000, indicating that value of subtract is not known. So you have to include one command to the loader saying that insert or add the actual value of subtract at the corresponding location. So what is the location corresponding to subtract? Please note the instruction jsub subtract begins at the address 0004. Okay, 0004 is a location wherein 4B is placed. And what is the location for 000000? It is one more than the address 0004, which is 05. So the modification record indicates that at the address 000005, add the actual value of subtract to the field which is 5 half bytes in length. So that is all with respect to the processing of or generation of the object code corresponding to the program main. The last record is E, indicating the end of the program and also indicating the address of the first executable instruction, which is 0. It is 0 here. Similarly, the object program can be generated for other two control sections. The next control section is add it. So we have the header record here, which begins with H followed by the name of the program. Name is add it. Starting address again for the control section is 0, and the length of the control section is, you can see it here, it is 0011. There is no xdef statement here, so we don't have any defined record. There is an xref statement, so we need to label all symbols in the refer record here. So R followed by x1 and x2. Following that, we have the executable instructions, which has to be placed into the text record. So we begin the text record with T followed by starting address. The starting address is 0000. And what is the object code? Object code is 0310000. For this instruction, we have inserted 0 in the address field because we don't know the value of x1. So in order to handle this instruction at the load time, we need to include one modification record saying that add the actual value of x1 at the location 000001, which is 5 half bytes in length. Moving ahead with the next instruction, which is add x2, the object code generated will be 1B1000000. So I have placed it here following the first instruction. Again, one more modification record has been created for add x2, which is M followed by starting address. Please note, add x2 begins at 4. The address field begins at the address 5. So it is 000005 followed by the length of the address field. What is the length? Length is 5 half bytes. Followed by the modification. What is the modification? We need to add the actual value of x2 to 0 to get the correct value of the symbol x2. After this, we have STA sum, which has to be placed in the text record thereafter. The next instruction is sum reserved 1. Please note, no object code has to be generated for this. So I have to terminate the text record here, because after that we have a storage space, and initiate a new text record for the next instruction. We have one more instruction, that is rsub. And what is the starting address? rsub instruction begins at the address E. So the starting address should be indicated here 00000E. Followed by the length. Length is not known now. I'll just put the code. What is the code? Object code. Object code is 4F. So we have 4F0000. The length is 3 bytes. So there are no other instructions. This is the last instruction in the program. So I can insert the length here. Length is 3 bytes. Okay. We use 2 columns to indicate the length, 6 columns to indicate the address, and this is the object code itself, which is 3 bytes. Please note, I have not explained about this 0E. This actually indicates the length of the object code in the current text records. This is 4 bytes plus 4 bytes plus 3. 4 plus 4, 8, 9, A, B. So this should be B. Okay. Finally, we write the end record. Generally, the convention is to write the starting address in the end record only for the first control section, leaving the address empty for other control sections. So please go back to the main program. Here I have inserted 0. This indicates the beginning of the program. We don't insert, generally don't insert the starting address for the remaining control sections. So we are done with the generation of object program for added. Next, we shall proceed with the generation of object code for subtract. So getting back to the assembling of the third control section, subtract, we have the header record which begins with H in the first column, followed by the name of the control section, which is SUBTR, indicated in 6 columns thereafter. Following that, we have the starting address. Starting address is 0. Remember, the starting address for every control section has to be set to 0. Actual load address can be obtained by adding to this 0 whatever the load address is. The length of the control section follows the program starting address, which is 0011 for the control section SUBTR. Following the header record, we need to see what is there in the source program. Here we have xref. We don't have an xdef statement, so no defined record has to be written. Next, we have to write the refer record. Refer record should label all symbols that are referred to in the current section and which are defined elsewhere. We have 2 symbols here, x1 and x2. So we label those symbols in the refer record. Each symbol is provided 6 columns, so I have left some space here, and the refer record begins with the alphabet R. Following the refer record, we have the executable instructions which needs to be written into the text record. So I initiate the text record with T followed by starting address. The starting address for the first instruction is 0. So 0, 0, 0, 0, 0, 0 followed by the length. Length we shall insert later. After that, what do we have? We have the first instruction 031 0000, which is the first executable instruction. Please note this is a 4-byte instruction and the value of x1 is not known, so we have inserted 0. So you need to leave one modification record. M followed by the starting address of the field that requires modification. The field that requires modification is the address field corresponding to x1, which begins at the address 1 more than the address here, which is 1. So M followed by 000001 followed by the length in half bytes. The address field is 20 bits in length, which is 5 half bytes. So 05 followed by the modification flag. Modification flag is plus, indicating we are adding the value of the external symbol, which is the external symbol in the instruction. It is x1. So which is x1. So after the first instruction is processed, the next one is 1F1000000, which needs to be inserted into the text record. Does this require a modification record? This requires because x2 is an external symbol which is not defined in the section. So we have inserted 0. So we have to leave a command to the loader saying that insert the actual value of x2 at the address corresponding to x2. What is the address corresponding to x2? It is 1 more than the address here, which is 5. So M followed by 000005 followed by length of the address field. Length is 20 bits, which is 5 half bytes, followed by the modification flag plus saying add the value of this actual value of the symbol x2, external symbol x2. So plus x2. The next instruction is 0F2 000. So 0F2 000, which is 3 bytes. There is no modification record is required because we have completely assembled this instruction. After that, we have diff reserve word 1, which says reserve the storage space. So you can't put 4F0000 here. That is the end of the current text record. What is the length? 4 plus 4 plus 3. So 4 plus 4, 8. After 8, we have 9, 10, and 11. After this is 4 bytes plus 4, 8 bytes, 9AB. So length is 0B. I have inserted the length following the starting address. So we are not done with object program because there is one more instruction, rsub. So I initiate a new text record. The starting address will be rsub is located at 000E. So you need to insert 00000E. And the length, we just have one instruction here, which is 3 bytes. So I'll insert the length also here, 03. And what is the object code? It is 4F0000. Finally, we write the end record because after this we have the end instruction indicating the end of the program. So end of the program is indicated here. So this is the object program for each of the control sections. First one is shown here. So I have a modification here. I have wrongly put the code. So 07. Here it's D, and we can't put 4F here. It's T followed by this. Similarly, we can't put 4F here. It's the control section subtract T followed by E and 4F00. So this is the consolidated object program for the control section main for add it and subtract. Also, since I have removed 4F, this will be 4B. All of you please go through the object program generated for the control section main, add it and subtract, which I have explained in earlier 6 slides. So that is all about the generation of or handling of the object programs during pass 2 by the assembler. Next, we shall go through few of the illustrations of handling the external reference in the context of different programs. Specifically, I am going to discuss how a symbol maxlen is handled in 2 different control sections in the example that follows. Okay, consider this particular slide. We have the first control section, that is copy, and the second control section, namely RDREC, which stands for read record. I'm specifically interested in processing the instruction maxlen EQU buffend minus buffer. So that is, we need to define the symbol maxlen, whose value is given by the EQU directive. EQU is as an assembler directive which assigns a value to the symbol, and the value is the value that is given in the operand field. In the operand field, we have an expression buffend minus buffer. So already we know that buffer has a value 0033. Buffend is not defined here. So what is the value of buffend? Buffend is given by an EQU directive, and its value is given by star, and you know that star indicates the current location counter value. So what is the current location counter value at this point? It is 0033 plus we are reserving 4096 bytes. 4096 bytes is given in decimal, and its hexa equivalent is 1000. So the updated location counter value for the instruction buffend EQU star is 1033. It is 0033 plus 1000, which is 1033. So now we know the value of buffend and buffer. So we can calculate the value for maxlen. Maxlen is computed as, how do we compute the value of maxlen? It is simply 1033, that is the value of buffend, minus buffer. Buffer is 0033, which is 1000. So maxlen has a value 1000. So this is regarding the handling of maxlen in the control section copy. We don't have any issues in computing the value for maxlen because both buffer and buffend are defined in the current control section. Now what about the same instruction in another control section, namely RDREC? Please note, the control section RDREC labels buffend and buffer as external symbols. Why? Because buffend and buffer are defined in the control section copy, not in the control section RDREC. And in the previous control section, maxlen is defined by the keyword EQU. It is given by the directive EQU. Here maxlen is defined is a symbol that appears on the constant that is defined, whose value is defined by the expression buffend minus buffer. Please note, here it is EQU, here it is word. What does the word assembler directive mean? It means that the instruction will reserve one word of storage, and the allocated storage will be initialized with the value that is given in the operand field. What is the value that is given in the operand field? It is buffend minus buffer. So we need to see what value is generated for this instruction. Also, we need to see what is the value that is assigned to the symbol maxlen. So how do we assign the location counter value for maxlen? See, consider the previous instruction. We have input byte x f1. The byte is an assembler directive which generates a character constant or a hexa constant. In this case, it indicates a hexa constant because the constant f1 is indicated by x. So hexa, in the sense, each character here is indicated using 4 bits. So 4 plus 4 is 8 bits, which is 1 byte. So this indicates a 1 byte hexa constant. So the updated value for the next instruction will be 0027. This is 0027 plus 1 byte, which is 0028. So in the earlier case, value of maxlen was given by buffend minus buffer. It is given by the EKU directive. So value is computed as the difference of buffend minus buffer. In the current control section, that is in the control section RDREC, value of maxlen is computed using the location counter value, which is computed as 0027 plus the amount of storage space allocated by the previous statement, that is input byte x f1, which reserves 1 byte. So it is 0027 plus 1, which is 0028. Please note the differences in handling the value or assigning the value for the symbol maxlen in the two control sections. Here, buffend and buffer are both symbols which are defined in the same section, and using those we have to calculate the value of maxlen. Here also, buffend minus buffer gives the constant that is to be generated at the address 0028, and the value of maxlen is the location counter value, which is computed as 0027 plus 1. So the object codes generated for maxlen is shown here. See, how do we generate the code for the instruction maxlen word buffend minus buffer? The constant to be generated is given by the expression buffend minus buffer, but we don't know the value of buffend and buffer, so we insert zeros in the place 0028. But that is not sufficient. At the time of loading, you need to add the value of buffend and from 0 with 0, and the value of buffer should be subtracted from that value. So please note, in the object program for RDREC, you need to have two modification record, one indicating that the value of buffend should be added, and the second one indicating that the value of buffer should be subtracted. You need to have two modification records. And now coming to the external reference processing with respect to control sections. Generally, it is possible that the same symbol could be defined in two different control sections. So in such a case, if a program has multiple control sections, and if a symbol is defined in two different same symbol is defined in two different control sections, it is important that the assembler maintain or remember in which control section the symbol is defined and what is the value in that particular control section. Say you have a symbol x1 in control section A and the same symbol x1 in control section B. So it's important that when you say x1 in the control section A, you keep track of what is the value of x1 in control section A. Similarly, you keep track of what is the value of x1 in control section B. Second thing is, it is important that whenever a program refers, a control section makes a reference to a symbol, the symbol should have been identified as an external symbol using the exdef statement, and it has to be whichever control section makes a reference to a symbol that is defined in another section, it should be labeled using the assembler directive xref. So if there is an attempt to refer to a symbol in another control section without being labeled in xref, then it should be indicated as an error. So any attempt to refer to a symbol in another control section must be flagged as an error unless it is labeled in the external reference as an external reference in xref statement.